This conference will now be recorded.
This training is on system architecture exploration. I'm your host Deepak Shankar, and I'll be working with you in helping you understand the methodologies involved in system level modeling and model-based system simulation, and also how to use Visual Sim in constructing models, doing analysis, and also doing trade-off studies to help you create a highly optimized architecture. Before we get started, I'm going to talk a little bit about the resources available. During this session, there is a chat window, as I mentioned earlier, and there are application engineers available to help you and to answer any questions. In addition, after the session, you can contact info@wilbursdesign .com, and there are application engineers that can respond to your questions. Many of you have probably downloaded the software and have it installed. If you have any problems, send an email to info@wilbursdesign.com and we can help you address any installation related issues. Now, one of the things that we have is a very large training video package that is available on YouTube that you can go to and play at your leisure and understand more details about all the different topics that I'm going to cover. Now, the additional tutorials that I have listed here are specific to some of the home tutorials that we'll be assigning at the end of this session. And we'll be going over some of those right at the end of the session. With this, I'll get started to talk about today's agenda. As you all know, we'll split this into two sessions. Today's day one. We're going to focus on the methodologies involved in architecture exploration and in system modeling. And then we're going to look at pre-built models, do analysis using pre-built models, and then go through some of the basics of Visual Sim, helping you understand how these basic components, how this basic methodology helps you in constructing models and doing analysis and presentations and studies and things such as those. On day two, we will review all of these, answer questions on your take-home tutorials, and then look at discussions such as how do we build custom components? How do we build models using components that are already pre-built or already available in Visual Sim? And we'll be looking at it at both the semiconductor level and also at the system hardware component level. A little quick introduction to Wilburs Design. We've been around since 2003, and as you can see, we've had a pretty rapid progression over the years. And we have a variety of customer base, variety of improvements to creating newer products and capabilities. This current version of the product you're seeing came out in 2015 with a considerable amount of and there's been considerable amount of upgrades that have been happening since that time. Here's just a little bit of a listing of some of the customers that we have with Wilburs Design. And as you can see, it's a broad area of applications extending from semiconductors, high-performance computing, defense, and automotive. A quick look into what Wilburs Design offers. Wilburs Design offering is based on a core of Visual Sim software with the libraries that go with the software. We have a quick start program that helps you get started by providing training and continuous hand-holding support. In addition to that, we have modeling services which can extend from building basic components that you can use to assemble your models, or we can build the components and models, or we can do complete system analysis and just provide you results and reports. These are some of the products that have been built with Visual Sim. At the last count, I think about 250 projects have been dealt with using Visual Sim. Before we get started, talk a little bit about Visual Sim. The core of Visual Sim is a graphical modeling environment that can be used for construction, debugging, presentation, and also for documentation purposes. The models themselves are constructed using a series of libraries, and these libraries have been built considering different application segments, different requirements, and different types of analysis. The underlying this technology is a discrete event simulator that provides you the ability to get a time-based view of what is happening in your particular design. The key aspects of analysis includes performance, power, partitioning, and integrating hardware, software, and networks. The key applications that we're going to discuss today, there's a number of other applications, but really the key applications that we're going to discuss today are mapping of algorithms, such as say a radar or a communication or an autonomous driving application onto either an integrated system or say an integrated avionics system or a completely distributed, say an automotive system. The other aspect is really about architecting the hardware architecture. So it can be within an SoC or a processor, or it can be FPGAs, accelerators, and plus processors, and also the whole memory hierarchy, caches, IOs, and any other peripheral components. One of the things that we start off, or most of our customers start off with using Visual Sim, is the requirement for looking at what is the resources that and the efficiency of these resources when software task graphs are modeled. Today, most software task graphs are modeled looked at primarily as static verification or analytical model. Here, we're taking the software task graphs and really augmenting them with timing, with power, with performance, and providing a view of what the system is going to do when you eventually start picking components and really starting to do integration. The last one is developing totally custom design. So this is where you're coming up with new protocols, integrating your firmware with your hardware software systems, developing a variety of network topologies, buses, things that are fully custom and are specific to the performance and power consumption of your system. System simulation with Visual Sim Architect requires you to be looking at a variety of analysis. So anything from throughput studies to failures, to buffer occupancy of your memory, to power planning associated with what your board or your chip may require, all the way to capacity planning of your network or your complete, say, your VME backplane. I'm not going to go spend too much time on this, but you can actually see this on our website. We've got probably the largest collection of modeling libraries, and this is something where we keep adding one or two components every single month. And the purpose of doing this is to ensure that if you as a customer have a requirement, there's a model that will help you get started with that requirement. So you can actually see explanations and detailed discussions on these models when you get on when you get on our website, and also when you download the software and take a look at that. Some case studies. We've got a large number of case studies, probably a last count about 300 or so. Variety of applications: defense, automotive, processors, high performance computing, whole variety of application segments. Now, before we get started with modeling, just let's go over what system modeling is all about. There's a lot of definitions, and we're going to put in the specific one that we're talking about. It's really about architecture exploration. What this means is optimize and validate the specification before you start development. For example, you're going to be doing timing or throughput analysis, which gives you a performance view of your system, or it can be a power measurement where you're looking at the energy consumption, you're looking at the battery usage, looking at spikes for thermal consideration, things such as those. Then comes the functionality. It can be arbitration, scheduling, logic, or even certain math functions that are required as part of your design to look at all the conditions we accurately met, be it on a failure level, be it on trying to meet the efficiency levels that you require or any other customer attributes. Now, before we get started with looking at a variety of methodologies, let's look at a basic system. The system we have in place here has got two CPUs, an IO and a DSP. It's got two bridges and, two buses and a bridge in the middle. What we're going to do is we're going to pick up some complex behaviors in the form of applications with tasks and map those against this hardware platform. Now, realize that there's only a limited amount of resources in every one of these components, and they have to be scheduled or arbitrated such that they can meet the timing and the power deadlines. If you take these tasks, they're really considered in two parts. Part one is where you map these tasks onto these devices or resources. The second one is the transfer between the tasks. So for example, over here, if you look at these tasks, each one is getting mapped to one or more resources. And then there is the communication or the transfer between the resources. So the processing within a device, and then there's the transfer across devices. Now, when you really look at it, there could be the first packet here, or a second request here, the third command here, and the fourth transaction can be here. So at the same time, all four can be scheduled out, and they could also have multiple things buffered in them to be able to process it. So any changes to the topology, any changes to the clock speeds, things like that, will have a huge impact on your system. Now, this is when you have a single task. Then start adding multiple tasks, same process. You have the task being assigned to resources, and then there's transfer between the tasks. Now you start to look at anomalies. Is there any way where if I put in, say, a specific flow, does my performance dramatically alter? Or if I change the mapping, how does it change? So now I'm going to walk over to Visual Sim and give you an introduction to the tool. So this is Visual Sim Architect. I'm going to go into a lot more detail later on, but for now, I will just talk about some of the basic entities. You're going to see the libraries here. You drag and drop components from the libraries to construct up these models. So if you have two CPUs, two buses, which is same structure as you saw in the block diagram right over here. Now these two tasks are mapped as two software applications with a workload, with independent workload for each one. Outside of that, you've got analysis tools, parameters, power, and a whole variety of other components. I'm going to go ahead and run a simulation so we can look at various aspects. So when you run a simulation, you can see dynamic execution. You can also run this in the background mode where you can just spawn this off on a large server farm and get results back. Now, here what you're looking at is, for example, this one is showing me the power consumption. If I click on the dots here, I can actually see at what time different elements were turned on and what times they were turned off. The red line shows me the what is the average. Now, in addition to that, this shows me the latencies of the various tasks that we're executing. This shows me the split up of what we talked earlier, which is, how much of it is processing and how much of it is transfer. And finally, we also have some textual data. Here, for example, shows me the DSP here, what was the utilization, the delays, the number entered, exited, anything rejected, and the buffer occupancy. So as you can see, not only do you get to build the model, but you also get a whole bunch of predefined reports that you can utilize. Now, one of the things you can do is as I mentioned, once you run these simulations, collect all the data, you can then plot them using our post-processor on a single plot here. What this shows you is I've got the same model. First time I run it at 200 megahertz, the second time at 400 megahertz. And what I want to do is try to see the worst case and the best case execution time, and also look at if there's any sort of unpredictable operation. So here you see the best to worst case for the 400 megahertz is between 1 and about 1.25 microseconds, while for the 200 megahertz goes from 1.1 to 1.5. But there are some conditions where you can see the 400 megahertz is actually got a higher latency than the 200 megahertz. This indicates that there are certain scenarios or certain reasons that could be buffering, or it could be that the processing requirements with the memory requirement is taking much longer in a certain sequence of things, especially when you have a faster bus. So when you overall look at this design, you find that the range of the 400 megahertz based architecture provides you almost a 50% plus range from your worst case to your best case execution time. So if you consider that and take that as a major discriminator, you're going to find that the range here is of the 200 megahertz actually much better. So in this particular case, the 200 megahertz architecture is preferred, and that's what will be considered in this design. Now that you know what Visual Sim looks like, what are the types of modeling you can do with the mapping and the hardware architecture, what we're going to look at next is we're going to look at the aspect of methodology. There's really three different methodologies and there are three applications. The first one is where we look at an ingress to an egress for a fully custom architecture, doing it at a high level without worrying about the exact implementation, like I'm selecting a Xeon processor, I'm selecting an ultra-scale from Xilinx, or I'm using a DDR4 from Micron, things like that, but rather looking at it at a pure functional level. Then we're going to look at the software tasks and then look at an SoC down to timing and cycle accurate by selecting an A53 from ARM, selecting a DDR3 with an AXI bus and things like that. Then we're going to look at mapping software applications on a pre-existing hardware platform. In this case, a Xeon from a single board computer from Mercury using Xeon. And then look at some failure scenarios. And also now, once you have these fully mapped software applications on hardware platform, looking at the extraneous things, for example, looking at the battery, looking at the network interface, looking at the communication at the modem level, and seeing how each one of these have an impact. So starting off with the flow control, in this case, what do we have? We have a series of ingress ports feeding into a series of egress ports, and there's some muxes and demuxes, and there's some intermediate flow control. There's also a credit from egress to ingress. So what are we looking at here are the things we could be evaluating. One is what's the rate at which data can come in, what's the buffer occupancy, what is the credit policy that you want to deploy, and then of course, what is the scheduling algorithm here to select from one of these channels before we send it out. So now what I'm going to do is I'm going to move over to Visual Sim and bring up this particular model. So this is the model constructed in Visual Sim. You can see this is the traffic. There's the two separate independent channels, and here we actually define which channel it's coming on by specifying a queue number to specify which one. This is a queue associated with the ingress. That's a queue associated with the egress. There's the intermediate stages which you're not going to look at, and that's your scheduler that handles both the scheduling and the credit policies. What we're going to do is go ahead and run the simulation based on the initial specification to see what's going on and see if the architecture that we originally planned works for our requirements. One of the things you notice right off is that the buffering is constantly increasing over here, and it actually reaches a 30. Now here, the latency is pretty much over here because I can see that through my histogram that most of it is right here, but then I see a long tail, which is what you're seeing over here as well. So what I'm going to do is, originally I started off with a round robin. I'm going to change this to use a deficit round robin. Same model, I'm going to run and look at what's going to happen. And one of the things you notice right off the bat is that the buffering just shot through the roof and went over 50. I think 50 was the highest point here. So after that, we're starting to lose packets, which is what you can see over here. A lot of activity, and then it kind of dulls out. And you can also see the latency histogram range is much greater for a large set of values compared to what we saw in the earlier designs. So we're going to keep the round robin. Then what we're going to do is try some other types of experiments. So for example, one of the things we're going to see is the Q depth is 100. So we're going to increase this to maybe 25. So, until it fills up to 25, you can keep sending stuff through. So we're going to do that. And then also what we're going to do is increase the number of channels. So we're going to go from 15 to 25 here. So which means I got 25 here, 25 here, and they get mapped to a common 25 over here. So we've made 3 changes, gone from deficit round robin to round robin. We have changed the threshold, that's the credit policy. We went from 5 to 25, and we changed the ingress size to 25 from, I believe it was 15 or so. So we're going to go ahead and run it to see what really ends up happening. You can see they're pretty flat over here. Actually, here's a key thing. Notice that the buffering keeps increasing, but not at the rate it was doing earlier. If you notice, the deficit round robin was at 50. This was, the round robin was 30. Now we've dropped it to about 15 or so. Again, you see most of it is over here, which is what you can see here with some spikes. What this tells me is, irrespective of how much I change the threshold, increase the number of channels, increase the Q depth, we're still going to start seeing buffering, and it's going to keep increasing. So really the only solution I really have is I can do 2 things. One is I can reduce the clock rate over here. Oops, sorry. I'm going to go from 20 megahertz to 20 megahertz to 10 megahertz. And I can also try to see if I can cut back on my threshold right here. So now what I'm doing is 20 megahertz. So rather than 20 megahertz, we're going to come down to 10 megahertz here. And we're going to try to rerun the architecture to see what happens. Are we getting any performance? So even at 10 megahertz with the with the slower rate, I think I made a mistake here. Get the in rate to be here. Okay, so let me make it 10. Oh, that's a mistake. So if you notice, I realized that I had a mistake just because I could see the plotting and realized that there wasn't a whole lot of changes where I would expect at least a little bit of a change. So this gives me some ideas as to what's happening. Also here, I can look at this to tell me what was the task latencies that were happening. Plus, every block as it goes through. So this is ingress 1 to ingress out, X on, and then there's X off, and there's the egress. Tells you when I came in, when I left. Here's the interesting thing. Almost all of them are now within this particular range here. And as you can see here, these are the 2 big spikes. So obviously now the buffer occupancy is sub 1, which means there's really no occupancy at all. And I'm able to push my data through. So the obvious thing is somewhere between 20 and 10 megahertz with an ingress size of 25 channels and a threshold of 15 is what would allow me to be able to run this particular design. So if you notice here, we have all the aspects of my architecture, the input traffic, the ingress ports, egress ports, and then the flow control and the credit. And here what I've implemented is the scheduling policy. So this one right over here is my round robin loop. And right over here, this small portion here is the credit policy, which essentially is I'm looking at the egress using this function called a regex and seeing if it's below a threshold. And right then and there, I know whether I have my credit or I don't have credit. So just by adding this function, I automatically get that capability. Now, one of the key things here is we have not specified what processor this is running on. Are these all going to come from a single pool of memory, or are they going to be, for independent memory? So now that you've seen the functional, you know what is required. The next step is to start looking at the more hardware aspect. So as we go back to our design over here, I'm going to go ahead and close this model. As we go back to our design over here, we're going to now look at more details on the software, which is the scheduling algorithm. We're going to narrow it down there. This is the task graph. So what is happening is, just like you saw, we got ABC, 3 flows or 3 states. Starts off with state 1, has to have 3 instances of it, with each one generating certain tokens that are fed into the second stage, which both of them have requirement of 3 tokens, and then each of them send an output, and then the C has 2 tokens. So as we build a model for this, what you see is, unlike task graphs that have been done in the past, which are mostly analytical or based on looking at, as it goes through every task, or is it missing certain tasks. What you see here is we got traffic that is generating at different rates. You got buffers, and you got these different flows and the dependencies between them. So now when I go ahead and run this, some of the aspects that are very critical here is the buffering. So I can see that the buffering is actually increasing here, which indicates that some of the scheduling is not okay. Also, here when I zoom into this particular thing over here, what you're going to notice is the time array is actually increasing here, 4.89, 4.99, 4.54. So what is happening is the latency is also slightly, it's very small and very subtle, but it's actually increasing. So you can see here in my array, going from B1 to B1 out, B1 in, B1 out, C1 in, C1 out. So you can see what's happening in terms of latency here as well. So using this, I get a good feel for, is my scheduling correct? Now remember, this is only that software portion of that functional model that you saw earlier. Now, as you can see, these were the plots. Now that I know, okay, here's what my end-to-end ingress to egress is, I know how my task graph, my software is. Now I start putting in the hardware. In this case, I'm actually designing the processor. My goal, I do have some deadlines, some requirements. One is the power has to be less than 1 watt. And the second thing is got to hit at least 20,000 frames. And this is my hardware architecture. Now, there are 3 explorations that I want to look at. The first one is all tasks are deployed in software, or I can take some of those tasks and implement them in hardware accelerator. Or the third thing is I add power management to the same thing. Now, the IP-based modeling, when I look at this, what I see here is I got the processor, accelerators, buses, memories, power management, and these are my 2 different use cases. So now I'm going to move over to the model. And this is the same model we have. You can see the 2 different use cases, the hardware platform, and then of course we have a concept called hierarchical modeling, which is you can put these things into into containers that can have more details. In this case, I got an ARM and a move core processor, and then at the top level I got a bus and the DRAM and things like that. Now, one of the key things is all the blocks that can be customized for the user is provided as fully opened out for the user to view all the details. So you can actually see all the internal details of what is happening within my particular system. Now, also have the hardware accelerator here. So first run, I'm going to go ahead and run the simulation where I put everything in software, and I'm going to see what's going to happen with the particular design. So there are 2 aspects that I'm really interested in. The first one is this here on the power, and the second one here is on the number of frames that I can process through this particular system on my display. So here you notice the power is always pretty much, except for the small spike at startup, it's pretty much below 1 watt of power. It's even probably 0.95. And you can also see here the analysis, which will come up with the number of frames per second, and you'll come up with, there you go. It's about 13,000 frames. So it actually reduces down as it goes over time to about 12,000 frames or so. So I want to see how much more performance I can get. What else can I kick in? For that, what I'm going to go ahead and do is take this one, rotate frame, and I'm going to move that from software to completely hardware. So what this means now is that I've gone from something that is entirely done in software on the ARM to something where I take some of these components and implement them on hardware accelerator. Now I can pick all of them, but I know that rotate frame, just looking at some of the statistics, other stats that I didn't show you, that I know that this is consuming the most amount of clock cycles. Same model, I'm going to go ahead and run the simulation. Now, one of the nice things you'll notice is we're running for about 20 milliseconds, and it takes approximately about 10 to about 20 seconds to run the whole thing. So, and you're running this at cycle accurate modeling accuracy, timing accuracy, and functional accuracy of exactly implementation of certain hardware components. Now, here, what am I interested in? There are three things. The first one is your overall power consumption. The second one is the number of frames. And the third one, which is a new entity here, which is my hardware accelerator. So I want to see how much of power is being consumed by hardware accelerator. So as you can see, spikes up every time it wants to want to execute the hardware. And then you can see that it comes down to a standby mode. One of the things you'll notice here is that the power spikes up. It's almost at about almost 1.2. So there's almost a difference about 20% in power between going with pure hardware, going with pure software with one accelerator block. Now here, you can see just by moving that rotate frame over the hardware, you can see I'm almost doubling the performance. So we went from 13,000 to 26,000 frames. Now I'm going to say, hey, this is a good number, but let me see if I can reduce this. What I do is I go back in here to the power table, and I'm going to enable this power management right over here. And then I'm going to go ahead and rerun the same simulation. So notice here, even the last time around with the functional model or task model or even the hardware platform and this, the same model can be, you can try out different experiments. And why is that important? Because requirements keep changing. Your architecture also evolves over time. So you want to be able to have a platform where you can quickly make changes without having to completely rebuild the platform. So here what's happening now is my performance is not dropped by a whole lot. Maybe it's about the same. But you can see now I went from 1.2 to almost hitting 1 here. There's almost obviously some ups and downs, and that's really because the power management that I set up was, after I'm done, I drop down to my standby state. I wait for about 1 millisecond, and then I drop down to an idle, almost a sleep state. So you can see that's exactly what this is conveying with this kind of gyration that you see. And after a while, it kind of levels out. This is the average power. It kind of levels out after a while. So using this, I can make a decision. Do I want to keep that hardware accelerator, which is increasing my power, but at the same time, doubles my performance? So now we're looking at not just that, I've got an ingress to egress and I've got a software task, but rather now I've got a hardware platform with very specific hardware components. So now what we're going to look at is, as I said, you can use the post processor to do comparative studies of taking one run versus another run. Now what we're going to do is we're going to map the software application onto a hardware platform. This is the case where we already have pre-existing hardware, and we're going to try different software tasks and try to see how we can map those against this hardware platform. So for example, the software can be defined as a task graph, can be a source code, it can even be a statistical model of the execution of the proposed execution of the software onto the hardware platform, or it can be a trace file from an existing system. So it can be a previous generation system, or it can be a slower system and we're migrating up, or for example, it can be having a slower memory or a different cache hierarchy, and here you have a different one. So you want to even bring in trace files from an existing system. So now in this particular case, what we're doing is we're looking at a radar application, starts from an ADC board, and you got multiple flows with dependencies and connectivities and things like that, and we're mapping it to a hardware platform. What we're interested in is the flow latencies at these 2 points, F10 and F12, the throughput, and what processors are actually active. So now we're going to move over to the model. So here what we have is, I'm not showing you the DSP, I'm actually showing you the Xeon based. If you open here, that's the details of the Xeon processor. I've got the processor, FPGA, PCIe, and then it's got the DDR memory as well. Now, the one of the things that is unique here is the concept of a dispatcher. The reason that this is important is because I have this thing and I have a lot of functions. I've got about 12, 13 functions that now need to be mapped over here. And remember that this could be a distributed or a multi-core or multi-processor, in this case a 12-core, but it could be other kinds of architectures as well. So, and it also depends on the type of data, where is the data located, all of those attributes. So a dispatcher becomes really useful because then I can actually sorry, this is one of the DSP, but I'll show you this. So you can have a variety of attributes. These would all be the attributes related to each function, and then what's the destination, which is which module, and which core on that, and what functionality, whether it's a link or directly to the core, and things like that. So the dispatcher can take care of this kind of modeling. So once you have the hardware platform, every time you have a new task graph, you draw it, and then you tell the dispatcher how you want to do the mapping of this particular design. So as you can see here, variety of stats we can get, and then based on this, we can make a decision as to whether this mapping is sufficient onto this platform, or we need to select a different platform. Now that you've seen the methodology of starting with ingress to egress, looking at the software tasks, looking at the hardware platform architecture, then taking the platform and mapping different software tasks, we're going to look at failure analysis. So what we have here is the 3 tasks. 2 are mapped to ECU1 and the other one is mapped to ECU2. So now what we're going to do is we are going to, sorry, give me 1 second. It looks like I didn't open up the model. So let me go ahead and open up the model. So what we're seeing over here is a network. There's multiple sensors on the network, and then there's multiple hardware platforms. We're going to just focus on this hardware platform on node 4. And what we have is the interfaces to the network, but also the hardware, operating systems, runtime environment, and runnables. Now, why is this aspect important? The reason this aspect is important is in addition to this definition of the software, we also have software analysis blocks. So here, for example, we check to see if each of the checkpoints, how many times they occurred, and what is the margin during which they occurred. Or, for example, for each of the checkpoints from this start to this end, what was the range? What was the latency range? So you can get a feel for exactly what is, whether these are all meeting their deadlines. So now what we're going to do is go ahead and run this model. And as you can see, variety of statistics. This is the one that's key, which is time between the ready to run and the actual running. That's a critical aspect. This one here tells me whether I detected a problem or everything's working correctly. And this is telling me what is happening on the hardware platform itself. So now what I'm going to do is I'm going to go back to my presentation. And we're going to look at the comparison. So this one here and this one here, the two we're going to really compare. And what we're going to do is look at the ready to run versus running versus here the ready to run versus running. What you get to see is the latency is constantly increasing with the fault that was generated. There were 2 types of faults generated. One was the schedule table was corrupted, so it modified the order in which the software instances were executing. And the second one is some of the values that were changed, which caused some of the sensor data to look different, and so the computation also increased, which caused the increased latency, which means here you were 80% utilization of the processor, where we get to almost close to 100%. So which means you have like no space available for it at all. Now, the last one that we want to look at is we've decided the hardware, we've decided on the software. Now we'll start to look at the external environment. So here we've got an AFE with a RISC-V core, Bluetooth, and then we got network hubs and data centers. So some of the things you can look at here is where do all the processing here, or I shift it over here, or shift it all the way here. So that one, because that has an impact on my data modem activity. You know, how many times I'm going to turn on, turn off, transit, you know, advertise, wait for data, things like that. The other thing is that, you know, if I put faster cores or, you know, more memory, things like that, my battery is going to get affected. Now you got the hardware, software locked. Now you're looking at how do I schedule these things such that I get maximum usage and maximum battery life versus, you know, sending more data across the network. So when I look at this model here, I'm just going to bring up this model. So this one here, what we have is multiple devices. You got a large number of devices here connected to network hubs that are then connected across the internet till they reach the data center or the server. Now, one of the key things over here, as I showed you earlier, is the hardware is included. We even have now the protocols being modeled. When I go into this one here, you can see the entire Bluetooth implementation right over here, with all the different states and transitions. And this is a BLE, so the low power board is probably the most important thing right here. So then, but in addition to that, we also have the battery model, which here what it also shows you is, you know, the statistics, but here's the charging, the consumption, and also here's where you have like thermal shocks and external aging factors that are contributing to the design. And then, of course, the actual consumption of the battery workload. So the this particular model provides you a starting point for you to build up on different battery designs, like right over here. And you can also see there's a charging aspect, and then there's the selection of the battery also. So not only now are you working on the hardware software, but you're starting to look at the network, look at the battery consumption, and you're looking at you know, even the internals of battery. How if I start adding more spikes, how does that increase my or reduce my battery life cycle? You can look at all of those kind of aspects also. So with this, you now understand how you can assemble models, how you can do your analysis, what are the types of analysis or studies you can do. Now what we're going to do is we're going to be looking at what do we do after we have this model. And one of the key things we do is we do an export to web. And what that means is that we now are going to be generating documentation out of these particular models. So the documentation is going to involve where we're going to actually create the. So what this shows you now is it shows me all the parameters of each of the blocks, shows me all the details, shows me what's the mapping of each one with the timing values, shows me the workloads, also the power right over here. And then here comes the most important one, which is really about, you know, I want to see what's happening in the statistics. Shows me my average and instantaneous power, shows me the histogram on the latencies, and also the XY graphs right over here. So the documentation is now completely self-contained, and any other, you know, text that you've written into the thing also gets embedded into the same document. So now, in addition to running the simulation, doing the analysis, optimizing architecture, you now also have the ability to be able to generate documentation that can be shared either with your customers, with your partners, or things like that. This doesn't require Visual Sim or doesn't require any connected to the network or any of those kind of things. So this was a model you saw, and these are kind of the evaluations you were able to do. And these were the reports that we saw generated, which are the average power, the MIPS, the latencies, things like that. So now, having now fully understood about what are the different applications and what are the different things that you can do with Visual Sim, the next question coming along is how do we put them all together? How do we work Visual Sim to do that? At this point, I'm going to take a quick break and see if anybody has any questions, and take a look at you know, what are the what are the additional things that you might not be seeing or things like that. So Go ahead and ask your questions. I'll give a quick 30-second break, and then I'll continue on to building the model itself. Okay, so now I'm going to go ahead and talk about the basics of Visual Sim. One of the key things in Visual Sim is everything is self-contained in Visual Sim. So if you look at this, this is the opening page, and as you can see, all the documentation, training materials, the tutorials, the block documentation, the examples, everything, and even access to support, everything is included right here in Visual Sim. You don't actually have to step out to go anybody else to the web or any of those kind of things. So this is all self-contained here. Now, one of the key things is the different parts of the system. Everything from the libraries to the menu to the toolbar, which is important. One is because the simulation runs up from here, but also how you want to visualize the system. The individual blocks, either hierarchical or directly there. And of course, the plots, the analysis tools, the power management, the traffic generation, and the parameters. So everything has components that you can utilize to assemble up the design. Now, the key aspect of Visual Sim are the libraries. The reason that I can show you so many models and we can create models so quickly is because of the large library structure that we provide or we already have. So now let's start with the basics of understanding the basic structure, and then we can start building up the system. So the key aspect of Visual Sim is a threefold thing: parameters, variables, and fields. What it is parameters, and I'm going to walk you through this in model. So this is Visual Sim environment, and these are the libraries. So I can drag and drop a component. In this case, I drag and drop what's called a digital simulator. I can specify how long I want to run the simulation. I'm going to say 6. So what this tells me is Visual Sim runs on a per second. So which means if you want to do a microsecond, it's 100e minus 6. If I want to do a nanosecond, it's 100e minus 9. Similarly, data goes in bytes. If you want bits, it's multiplied by 8. And most of our hardware components run on megahertz. If you put 100.0, it means really 100 megahertz versus 1000.0 will give you 1 gig. So now that I set this up as a digital simulator, and the reason also we want digital is because later on when you see more advanced models, you'll see that they have synchronous data flow, continuous time, finite state machines, and things like that. So we're going to introduce a parameter into the whole swing. We're going to call it stop time. So rather than, and I'm going to put in the same value, say 6. So now, rather than having to go in here, I can just link this to this parameter over here, and I can say stop time, go get it over there. Now, one of the key things, if you notice, is the case sensitivity of the elements right here. So now what I've done is I've got a top level parameter which I've got linked over there. So these are parameters. Parameters are constants in Visual Sim that you utilize to run sweeps. So once you're happy with the model, you're debugged it, everything looks good, you can then go off and say, I'm going to run this on a batch and say run for like 100 variations to stop time or 100 variations to model seed, or different clock speeds or different algorithms, things like that. So next thing I'm going to do is bring in some traffic. And I'm going to set this to where we'll just run for a single one. We have this name here. And I'm going to set up a display so that I can view what the results are. So now I'm going to go ahead and run it. I'll be set up only for a single event. You can see now that I have this traffic. It tells me which block it came from, what's the ID, which is the incremental number, and the timestamp as to when it was created. Now what I'm going to do is I'm going to set this up, say, hey, generate 10 of these. And I'm going to go to fixed, which means every 1 second. So here we come to 1 second. So we're going to do every 10 microseconds. I'm going to do that and run it. So now what's going to happen is at 0, we got the 1, then we got 10, 20, 30, all the way up to 80 microseconds. Even though we're running to 100, we only need 10 of those, so we stop at 18 microseconds. So now what I want to do is I want to put in some details. So for example, the first thing I want to do is I want to have two of these. So put these, and I'm going to actually generate a behavior. So I'm going to bring this block here. I'm going to put this here. And here what I'm going to do is I'm going to write to one of the fields. So input indicates that it's coming in on this particular port here, which is the input port. And that's why we're using, so it's kind of the pointer to that, it's coming out of that port. The reason is you can actually have multiple input ports in the particular block. So we'll take input, and there's a field already in place called delta. And I will say input.delta is equal to, and what I would do is I would say 2.2 multiplied by input dot time multiplied by input dot ID. Okay. So I'm going to put this here. I'm going to connect it and send it out. Similarly, I'm going to copy paste this. I'm going to put it over here. Like this. And here I'm going to give this 2.6. So what we have here is two completely concurrent systems. And I'm going to change this where rather than starting this, I'm going to put this as 0.2. I'm sorry. Yeah. We're going to go ahead and run the simulation. Now what's going to happen is we're going to have two different plots come up. But unfortunately, what's happening is only one of these plots is showing up, the other one is not showing up. So it's like, what happened? Why is this working? Goes up to 90, but this one is not really working, it's not really doing anything. And we know that because this is traffic, so we know it's coming out of this one, so this one's not getting anything out. So now what I want to do is I'm going to go animate it. I'll run this. See activity, but I don't see any activity over here. So it indicates there's something wrong over here. So now the first thing I want to do is I want to go ahead and look at the attributes and see, we're running this only for 100 microseconds, but we see that this is 200 milliseconds. So let me change this to 0.2 e minus 6. Go and write the same thing. And now you can start seeing values pop up here. You can see what the now you can also see that the delta calculations are different for each of them based on those numbers that we saw over there. Okay. Now, one thing if I want to do more detailed debugging is I can right click on block and say listen to block. I do that, I can set up here. You can see every time some block goes through, you can see exactly what is happening through the block, what are the expressions, what's the sequence, what's the output value. I can see all of those details right through this window or this text editor over here. So it gives me a visual view of what is exactly happening through the entire system. So these become my first level of validation of my particular design. And as you can see here, we used parameters to link. We had traffic which generated these data structures. And if you look at these, data structures can have any number of fields. In this case, we just wrote the results here. But what I can do is I can create a new field called, let's see, my value field. Okay. And just like that, without doing anything else, I just added my value as a new field over here. This was the original, and this is my by value. So now it's very easy for me to go ahead and add and delete fields from my particular design. Okay. So now that you've seen this, there are a lot of other manipulations you can do. For example, over here, rather than writing it to a text display, I can go over here and say, you know, like I just want to print out the value of my value. Sorry, I want to print out my value, the field value called my value, and I'm going to send it out to a plotter right over here. So connect the plotter. So you can see it's a nice, cool, neat curve. I can even put dots here to look at more details, but I can essentially see this. Now, if I want, I can do this where I can do the same thing over here, which was delta. And rather than connecting it over here, I can connect this over here. So now, if you notice, there's a white port here, and that's one of the reasons why I'm able to connect them. If I was a black port, I couldn't connect to multiple of them to that port. I'm going to go ahead and run the simulation. And now you can see there's a divergence between these two right here. So now what I can do is I can actually plot multiple different traces onto the same plot. Of course, I can go in here and say, you know, like computation is a heading. I can say simulation time is what's on the x-axis, and I can say calculated value is on the y-axis. And now you can see there's more details and it looks clean to be able to present to someone outside. So that's the difference between parameters, variables, and data structures. Parameters are constants, cannot be modified during the simulation, while variables are single value that you can store in your particular model. So for example, over here, a variable is something which I'm going to go and create now. And rather than putting this into a field of the data structure, because it's really not related to the data structure, but rather it's a computation that anybody can use, I'm going to put this my value over here and give it an initial value of 0.1. So now what's happened is I've got a common local variable for this particular window. Now, variables work on 3 levels. The first level is where it's global to the entire model. And I would have set this in the variable list to say global, or local, which is only to this window. Or it can be something local where I can create something over here. I can say result A is equal to, and I can say my value is greater than 15.0, and I can say true colon false. And then over here, I can do result underscore A. So if the value is greater than 15, then it will actually print it out. Until then, it will not print it out. So we'll go ahead and run it. So notice over here, the value is never actually printed out. So which means that this calculation never gets to be true. It's always false, so it never goes through. So if I set this to not true and run it, so now we have an error. The input.myValue has an error because this field, no method found match, which means that field did not exist. This is where it was. Earlier on, if you remember, it was the field of the data structure, but now it doesn't exist. So now, why was this important? The reason it's important is because if you made an error, you'd have to go looking all over the code, but rather here the model will tell you exactly where the problem is and exactly what you need to go fix. We'll go ahead and run simulations, and now you can see we got our results back again. So at this point, I'm going to take another short break and allow people to ask questions. If there's any questions, go ahead and ask them right away. Okay, so now variables. What did variable do over here? We saw we had a local variable here, which is only there for within this block at the period that the block is executing. But we have this one here, which is actually stored up here. Why is that interesting? The reason is, say for example, we have a particular calculation over here, and we want to use that calculation over here. So right in this delta, I want to use my value. So now I don't want to have to like say, go get the data, come back, but rather I put it into register or into variable, and then obviously I can do my calculation right here. So when I go in here, so you can notice what the difference is because now I'm using that value. So just by now connecting with this one or multiplying by that, I get the actual performance here of the of the communication between these two completely independent flows. So that's the purpose of variables, which is that it can be carried. It can be like a central location where you can access it from anywhere in the model. So that's the major role of the variables. Data structure fields. So the fields, as you saw, can be dynamically created and removed. Typically, fields are something that are associated only with that transaction or with that request, meaning that it says what the command is, whether it's a read or write, or it's like what is the priority of that packet, or what's the size of the data, or what's the particular protocol, or is it a CRC value, things like that, which are only relevant for that packet. So once a packet is destroyed, it's not needed anymore. Those would be stored in fields of the data structure. Now, try to understand the usage. If something that you want to run iterations on, when it stays constant during simulation, then the best thing is to go with a parameter. Now, if you're going to be running these parameter simulations where you're going to set up a batch mode, you're going to run simulations, it's better to keep the parameter at the top level. So you don't have to have the difficulty of going top level dot block dot block dot block, and then you put in a value. So it's always very convenient to just put it up to the top level. If it's specific to the packet, image, signal, transaction, command, request, then you put it into the field of the data structure. Now, if it's going to change during the simulation and is required across the model, like we saw two separate flows and we took one value for one flow and brought it in the other one, then we use the variables. So now that you understood the basic infrastructure, we're now going to start talking about how do you define the traffic, processing, reporting. Okay. So traffic can be defined either as some sort of a distribution, kind of a custom development, or it can be used using a traffic reader. So we had a particular customer that had almost 180 million points that corresponded to maybe a little less than a second of transactions on a memory. And they wanted to run this through the model to see if there's any anomaly through that particular path, that particular trace that it ran. So that is something that you can do to try to identify on an existing system there's a problem, or if I take this and put it on a new system, how does it react? How does it behave differently than how it was on the existing system? So now that you saw the traffic, the next part of the traffic is related to two things. One is details about the traffic, and also making decisions. So it can be jump statements, can be control, can be other kinds of decisions. So we saw the expressionless block, and we saw where we could use that one. So if we go back here, if we saw here, this is the traffic, and of course, we can change to a variety of distributions. So I can set this to be, I can do something like this, so it actually shows up within this particular range. So you can see, oops, let me remove this one here, so you can see the value more reasonably. So you can see what the value is now coming on the output port. So which means, oh, we don't have a dependency. Oh, we do have a dependency, the time when it was generated. So when I look at this now and do a listen to block, so you can actually see every time it comes in, it's got a really calculated value. It's no longer just a sequential of 10, 20, 30. It's got different timestamps. Now, one of the things I can do here, if I wanted to, is I can remove this and say, you know what, I want to both plot it and I want to write it to a file. Then what I can do is I can click on this diamond here, bring that guy over here, connect this here, and also pressing down on the control button, I can connect this guy here too. So what the diamond does is now it connects all these three into one of the flows here. Go ahead and run it. And you can see here now, these were the times when these values came out, and that was the actual value. So this was the timestamp when it was generated, and then what was the value at those times. So it was the calculated value. So you can see all of these by setting up a display over here. Now, one of the key things about the block we just saw, called the expressionless block, I'm going to move that over here so it's easy for us to put in a smaller window profile. Here we go. So it is possible for us to add multiple inputs and output ports to this block. So I can add here and say input 1, and then I can add another one and say output 1. This can be in, that can be out, and I can connect it. So now you can see but two. But here are the key things. all the values on the inputs have to arrive before I plug in this block. So for example, I click this. Notice I only get this output. I never get any output from here. So that's the first thing. So now what I can do is I can do this. And this, I can not only set this, I can set this to be like, 0.2345. It kind of gives me some really nice results. So now you can see that what had happened was earlier on, we were not getting any values. But now we've gotten value because both the inputs are there, but then it says output port list does not match the port names. So when I look at this, I notice that I've got only one output port, but here I got two output ports. So now I have to put output 1, and here I can put input dot time, and I can say true, which means no matter what, generated, like as opposed to the previous one where we had some conditions. And then what I'm going to do here is I'm going to remove this, connect this directly here, connect this value here. So now you can see this shows me when it was generated, while this one was a computed value. What I can also do, for example, is I can say, you know what, show me the entire data structure. So now you can see I can just print out the data structure. So it gives me that flexibility. Now, one of the key things with this block over here is it's a very sequential execution. The only if-else is this thing over here, which is called transitional if-else. Otherwise, it executes the code in a very sequential manner. This is completely different from this other model that you saw a little while ago, which was this one here, where the code is had whiles and fors and if-else and all these kind of nested whiles and things like that, which is a full-fledged programming environment. Now, results. There can be a variety of results. One of them is the resource statistics. We're going to look at that in a few minutes after we finish the resources. But the other one is the different type. We saw the histogram, XY plotters. We also saw the text displays, but where you can also take some of this display, and rather than viewing it, I say don't view, just save, and I can say model.txt. I can go ahead and do a save for this model. Go ahead. Simple model. We'll just give it a name too, and we can save it. So now when I go ahead and run it, notice the text display no longer appears. When I go into this one over here and go into this one here, you can see that's the model that just appeared. Or I'm sorry, that's the result that just appeared, and you can see the statistics being printed out. So now that you've seen all of these, you can see these are the different types of stats. Now that you've seen the parameters, variables, and data structures and how the fields work. You also looked at the processing, and you looked at the statistics or the reporting and the results as well. Now what we have to do is really the behavior and the traffic are really nothing to do unless you actually have a resource, which is your hardware and software platform. This can consist of anything from your processors, buses, memories, peripheral caches, I/O devices, your DMAs, or your RTOSs, your runtime environments, all of those kind of things. So when we look at resources, there are really two types. There's a time and there's a quantity based. Time can be divided into 4 types, which is one where I know in advance this is going to be the latency after I get to the head of the queue. So for example, if I'm getting on a network link or I'm getting on a bus, I know that once I get to the head of the queue, it's going to take me exactly data size divided by the width divided by the clock speed. Or I can be going into a queue that's going into a processor where I don't know in advance how much time it's going to take. There's going to be a delay, and once it's done, we're going to pop the thing out. The third one is a scenario where you have these different flows, like we saw in the very first model. You had like 3-4 flows, and in different parts of the flows, you get mapped to different parts of the system. Sometimes 4 times in the flow, you get mapped to the same system, same resource. This is kind of important because what's happening now is I can have the wiring all connect back onto the same block. So this is an important consideration, and if I do that, I need something that can be shared across all of these. This is what we call mapping to behavior. I'm sorry, mapping to resources. Then, of course, once you have the resources, say it's a processor, you might say, hey, I need more details. Like, this is my RTOS to my processor. Then processor needs to connect up to, like, say, memory or an I/O device or things like that. So you can extend the system resource as well. So what we're going to do here today is now we're going to actually look at this model in a little more detail. I'm just going to erase all of these. We've got my traffic coming in. And then the first thing is I'm going to I've got this output here. So we'll find over here, we're going to use this lower port. And here as well, we're going to use the entire transaction. So what is going to happen now? The first one, we're going to put in a queue. We're not going to connect anything to the first, anything to that one. And then this one is going to get a server. So what's happening over here is I'm going to call this the queue. And I'm going to have only a single queue. I'm not going to worry about priority for now. And then this one here is, I'm going to call it a server. But I'm going to give it some time value. I'm going to say, like 10.0 E minus 6. Okay. Now for this one here, I'm going to bring in a delay block. So this one here, as I mentioned, when it comes to the head of the queue, it's going across a bus, and you can describe the details. Now here, when I bring in the delay, I'm going to use the same delay, no difference, and I'm going to connect this. Now when it comes out, I'm going to bring in a diamond, put that over here, connect it, and then what I'm going to do is get a block called the const block. The reason I'm getting that is, and I'm going to actually flip it. So one of the things is every block, you can set up your appearances. So some of the blocks can be long, some of them can be short, some of them can be, like enough to split up all the input ports. For now, all we're going to do is just turn it horizontally. I'm going to connect it over here. And since we only have one queue, I can, connect this up like this. I'm going to go ahead and, oops, we forgot to put something on the output ports to take a look at. That, put another one here, and connect this one. Essentially, the performance of both is the same. I got only difference is the traffic is different in each case, but the latency is 10 microseconds, and same thing when it comes up here, it's 10 microseconds as well. So we're going to put this over here and put this over here. So notice the thing that is common here is that my latency is 10 microseconds right over here, and my input time to output time. Similarly, you can see my input time to output time as well over here, which makes it 10 microseconds as well. Now, I'm sorry, this showed me it came in and came out immediately. But now, one of the things that is different here is the fact that here I have some additional dependency. So it's not just that I come to the end of the queue and it's always a fixed number. Here it's actually a variable number. So I believe I can even do this, where I make it a random number and I go 10 E minus 6, or actually I can make it 8.0 E minus 6, comma 11.0 E minus 6. So now it's no longer a fixed value, it's a random number. So I can even generate jitters associated with that delay. So you can see now the values are actually changing even more relative to this particular design over here, which is nice and clean. So now what you're seeing is I've got something where I can either use a queue or a server. I'm going to show you an example that I built earlier this morning. And what you see over here is same design, the queues. In this particular case, I've got the traffic coming in. Now, rather than just going out popping it, I'm popping it from an input logic. And what this logic is I'm looking at the length of the queue of the index 1, which is the Q1 within that queue, and seeing if it's below a threshold, which is a parameter right over here. And if it's below a threshold, then I go pop, or sorry, achieves a threshold, which is, once I get to 5 packets, I go to this loop where I start, sending and popping all of them out at the same time. So now I have a scenario where I'm sending all of these packets, they're starting to fill out, and I get a bunch of them, and then I throw them out. Same design, but now what is different here is, rather than sending it all to one queue, I have a number of queues, and I'm randomly associating each packet coming into a different queue. Comes in, I start putting them into a different queue, but I also have a logic here, which is that I check my multi-queue and see for that particular queue, is it reached a threshold? If that one has reached a threshold, then I say, okay, now I can go pop them out, and I go, send all of them. So now the difference here is that this one has only a single queue, but now here, you have just a single input, single multiple. I got multiple concurrent queues running in the system. So when traffic comes in, I can assign it to one of those different queues. So same design, but now rather than having a single queue, I got multiple queues over here. So now that you've seen this, we're now going to go look at how we can describe it where I got multiple flows. So I'm going to bring in this block over here. I'm going to set it up. So I'm going to say, I'm going to 0.0, and every 10, I'm just going to give every 10 microseconds, there's going to be transactions coming out. And actually, I'm not even going to use this for now. I'm going to define a system resource, which is right over here, and I'm going to call it process. So this now becomes my processing unit, and right over here, I'm going to create 2 more of these. Oh, I want 3, this one 2. I'm going to give this a short delay, so I'm going to give this a 2.0 e minus 6. I'm going to give this a 4.2 e minus 6. So that's the delay for the first one, and everyone after that is going to get an increment from that point onwards. We got these 3. Now I got the traffic, I got the resource, but nothing to connect them. And for that, we have something called the mapper. So we're going to connect this, and I got 3 of these. So I'm going to say we're going to connect to process. This is task number 1. My time is we'll give e minus 6 by 10 microseconds. I'm not going to worry about priority. So only thing I want to change here is this 2. So I'm going to give each one a task number. I'm not going to do anything else. Now they're all going to come over here. So what I'm going to do is just look at the timing diagram on this particular device over here. Okay, now we have an error. So it says task time error. We're going to look into this, and it says that just to check the task time, there's an error in the task time that we're looking at. We're going to go back here, look at this setup, and we go 10.0 e minus 6. There was a value incorrect that's right there. I'm going to fix this, fix all of these. So notice I made an error and immediately it caught the error. So we're going to run again and see there's no errors. No, there isn't, because first task comes in, executes, second task, third task. 1, 2, 3, 1, 2, 3. So now what we're going to do is we're going to start adding priorities. It's going to be one for priority 1, priority 2, priority 3. Higher the number, higher the priority. So what's going to happen now? Notice now the plot changes a little bit. What's happening? First task completed, and then this the second task never came along because it's been queued up. But then you start noticing the third task is starting to fire here. Why did that happen? The reason it happened is because that has higher priority, and before that task is finished already, the next request has come for that particular flow there. So now what I'm going to do is for this one here, I'm going to reduce the processing time to say 6. So now what you see is, comes in, there's this one here, the next one came along immediately, then the second task completed, then 2 of these, now 3 of these. So variable number, because if you look at it, we've got this thing here, which is, starts off at 4 and goes to 10. There's possibility of, like some of them jumping in between. Now what we're going to do is, we saw this over here, this plot over here. You can see what it looks like. Now what we're going to do is we're going to introduce preemption to the exact same design. So now what's happening is 1 came along, but it didn't actually finish because 2 came along. And before 2 finished, 3 came along. So 3 is continuously, when it comes in, 2 comes in, 2 comes in, but there's priority here, and as a result of which the queue is getting reordered to provide number 3 the highest priority, then 2, then 1. So now it's every time I did this, when I change the values, the tasks started behaving differently. Now I'm changing the priority, and there's the priority also is causing these things to move. So now what I'm going to do is I'm going to take one of these out of the equation, and I'm going to replace this with something that has mutual exclusion set up. I'm going to set up mutual exclusion. I'm going to call this process, task number 2, priority 2. The mean time is 10.0 E minus 6. We're going to issue the task now. We're not going to queue it locally. Same thing, but what's different now is this one here has priority 2, which is greater than this, but less than this. But the key thing is, if this guy starts executing, he cannot be preempted. So here we go. Task 1 came along, got preempted, but task 2 did not get preempted till he completed. Then 3 finished, then again when 2 came in, he could not be preempted. So if you remember the earlier one, he was crunched a little and eventually had to finish. But no, he has to complete his task before he can get on to these other things. So same model, you can have multiple flows getting mapped, you can change your clock speeds, add priority, reordering the queue, add preemption, and then add mutual exclusion for preemption. So same set of blocks can do a variety of functions right here. People have any questions, feel free to ask these questions, or I can answer them during the presentation. Of course, there's other application engineers also standing by to answer some of your questions. So one of the aspects of Visual Sim is what's called quantity share. Quantity represents things like memory locations or indices, database, can be a parking garage with lots for cars, a variety of applications that can use it. Now, servers we saw was an active resource, which is, it's got a scheduling, which is FIFO or LIFO, and it has queues, a number of concurrent queues. When they come to the head, there's a delay, that it gets delayed and sends out. Queue, on the other hand, comes in, has a queue, it waits until it gets a pop. When it gets a pop, it sends it on the output port. Now, one of the key differences between server and queue is that delay in a queue is not predictable, while delay in a server is always predictable when it comes to the head of the queue. We saw the mapping and we saw the architectural components. We saw this over here. And essentially, you have multiple of these flows mapping onto a single resource. So now what we saw was a static map, but you can also do what's called a dynamic mapping. What that means is I can have something that looks like this. Let's bring in another one, and we'll call this process 2. And we won't turn on anything. We won't have preemption there. And we'll have here for the resource, we're going to say, we're going to generate a random number between 0, 1, and I'll check to see if that is 1. If it is 1, then I go to process 1, I'm going to process, else I go to process 2. So what I can do is not just do a static linking, but I can also do a dynamic linking. For a certain number of times I go to process, certain number of times I can go to process 2. Now, obviously in a real life, this would be a lot more complicated, but just from a demo standpoint, I'm showing you this functionality in this way. Then run it. So now what we have to do is show another timing diagram, which is right over here. Run this. So now you can see only one goes right through. Now notice here that there's some empty slots, and that's because some of them are being mapped here, but because the priority, they're not actually getting executed. Okay. So now that we saw that, there's differences. There's an additional block called a system resource extend. Not going to cover it today, but I'm going to just explain the difference. This one you can do preemption. This you cannot. This can be hierarchical, which means you can have one block linked to another one. So you can do like an RTOS to a processor or a runtime environment or processor, things like that. This one cannot. Of course, I can do an extension here where I can add more details on the extension port to say, include memory or IOs or, databases or things like that. One of the key things with this block here is I can do non-blocking, which means that if I come in and it's available, I process and send it on the output port, as opposed to blocking, which is if it's not completed, I wait until it completes it and then start the other one, next one. Statistics. So one of the key things of these blocks is the ability to generate a variety of statistics. So we have a block here called the resource stats, and we have all of these. So we're going to actually generate stats for all of them. We got process 2, and then we had queue, we had server. So you got 4 of these. And we have only a single queue in all of them, so we're just going to do this. And we're only going to generate one sample at the end of the simulation. And do that. And we need to write it out to a text display. Run the simulation. And there we go. So we generate the stats, and we're going to go ahead and look at it. So the server block is the one that's most heavily utilized. It's 99.378. But the interesting is 10 came in, 9 went out. There's only 1 buffer occupancy, but here's the latencies. Now, when you look at the queues, it's probably immediately coming out because we set it to trigger as soon as if the queue is free, immediately we can send it out for the delay processing. Process was 50%. Well, I'm sorry, process was 50%, 94%, process 2 was 50%. So this was where we were only sending occasionally, or 50% of the time, we were sending the first mapper to this one here. Mappers 1, 2, and 3 were being sent to this one. So you can see what the buffer occupancy is, my delays. And the nice thing is nothing has been rejected yet. Rejection means that my queue is full and now it's starting to overflow. That's really what rejection is all about. So just by entering this information right over here, I was able to get the statistics of all of these different blocks in this model. So we saw a variety of feeding in traffic, processing. We could send it to a bus or a network. We could do a multi-channel, which is, you saw that you could set up concurrent channels and then make independent decisions for each of the channels. And then, of course, we saw applications sending requests to a single resource as a core, but then you could also have 2 cores and then sometimes send to one, sometimes send to the other. We saw the preemption and mutual exclusion. We didn't see the power. We're going to see that on the next session. So now, before I wrap up, I want to talk a little bit about the tutorials. It'd be really good if you guys can work on some of these tutorials before the next session, because that way we can answer questions. We can also modulate the next session to focus on some of these aspects. So the ones that are best suited are the foundation, flow control, cache, and exploring. You'll be getting this email with this presentation so you can actually look at it, but just to give you an idea, they're all right here in the tutorials. You can click on it and you can say, getting started as the foundation, performance has the flow control, architecture's got the cache, and of course the network has got the usage. So they're all right here in the tutorial. Now, of course, there's a lot of other tutorials. If any of them, attain your fancy, you can also try to do some of those as well. And as I mentioned, there's online support or info at Wilburs Design. Both of those can get you access to our application engineers. So with this, I want to wrap up this session. Now, the next session will have more details in terms of looking at more of our pre-built building blocks like PCI Express, AXI-bus, or processors, DDR5 memory, or HBM, things like that. And also how to create custom blocks, look at power consumption, and also some of the infrastructure for you where you can share it across a large team. So now I open the floor to any questions people may have. I'll be happy to answer your questions.